Designing a global microblogging platform begins with calculating the load. We have 150 million daily active users generating, compressing, and consuming data simultaneously. At this scale, users publish roughly 300 million posts a day. That translates to an average of 3,472 write operations every second, with traffic spikes regularly hitting 7,000 requests per second. But the write path is only a fraction of the problem. This chart compares peak writes against the read path. Users scrolling feeds generate 350,000 read queries every second. That creates a strict 1,000 to 1 read-to-write asymmetry. For every piece of data written, it's read 1,000 times. Traditional centralized SQL databases fail under this specific constraint. The relentless volume of read requests saturates disk I/O, while relational table locks bottleneck the incoming write traffic. Operating at this magnitude is an exercise in calculating mathematical boundaries. The architecture must be explicitly designed to survive this exact imbalance. The first mechanical hurdle on the write path is identifier generation. Every new post needs a globally unique, chronologically sortable ID, generated at 7,000 queries per second across 1,024 distributed nodes, without waiting for a central database to lock and assign a sequence number. The solution is the Snowflake ID, a 64-bit integer computed locally on the operation tier, completely bypassing database coordination. This animation maps the Snowflake structure. After a single sign bit, the first 41 bits encode a timestamp. This block records the exact millisecond the post was created, measured against a custom platform epoch. The next 10 bits resolve the collision problem. They map to a specific data center and worker node, acting as a permanent machine fingerprint. No two servers can generate the same identifier. The final 12 bits act as a local sequence counter. If a single machine receives multiple requests in the exact same millisecond, this counter increments, allowing one node to generate up to 4,096 unique IDs before the millisecond ticks over. Because the timestamp occupies the highest order bits of the variable structure, Snowflake IDs are naturally sortable by chronology as raw integers. Decentralizing ID generation clears the write bottleneck and ensures that data inserts sequentially into persistent NoSQL storage without triggering expensive B-tree page splits. Once the ID is generated and durably saved, the system faces the problem of distribution. The post must reach the author's followers. This network graph illustrates the pure push or fan-out on write model. The system queries the social graph, locates the author's followers, and prepends the new post ID directly into each follower's pre-materialized Redis cache. When an average user with 200 followers posts, this requires 200 fast in-memory write operations. This O of N write amplification is easily absorbed by the caching tier. Then, a celebrity account with 100 million followers publishes a post. Under pure push, that single action demands 100 million distinct cache writes. The infrastructure collapses. Network connection pools exhaust, worker nodes max out their CPU, and the background message queues fill to capacity. A standard user's post sits stuck behind the celebrity's write storm for minutes. Pure push drops read latency to near zero, but the highly skewed math of social graphs ensures that outliers will routinely destroy the write infrastructure. To eliminate write amplification, engineers look to the inverse architecture, the pure pull or fan-out on read model. Here, the system performs zero proactive distribution when a user posts. When the 100 million follower celebrity hits send, the system executes exactly one write to the primary database. The write tier is perfectly protected. The processing debt is shifted to the read action. When you open the app, the system must dynamically query the graph to find everyone you follow and pull their most recent posts. This diagram illustrates the computational cost. A single user node sends out simultaneous requests to multiple database shards, returning disjointed blocks of data. The system must execute an OM log K temporal merge sort in memory just to render a single chronological feed. Now apply that heavy processing overhead to the global requirement of 350,000 read queries per second. The database shards saturate entirely and latency spikes into the seconds. Pure pull solves the celebrity problem, but guarantees complete failure under normal read volumes. If pull breaks the write path and pull breaks the read path, scaling requires a synthesis of both paradigms. This logic gate shows the hybrid fan-out model. Accounts are classified and routed through distinct pipelines based on a configurable threshold, typically around 10,000 followers. Users below the threshold follow path A. The system applies fan-out on write, efficiently pushing their posts to followers' caches. This secures sub-second read latency for the vast majority of the network's data. Outliers above the threshold follow path B. They skip the fan-out queue entirely. Their posts fall immediately into a dedicated, read-optimized celebrity pool, protecting the background workers from write storms. By treating data heterogeneously, the architecture explicitly caps the maximum cost of any single fan-out event at 10,000 operations. The final assembly happens at the exact moment a user requests their timeline. An edge service parallel fetches data from both architectural sides. The edge service retrieves the pre-computed Redis list containing standard posts. Simultaneously, it pulls any recent updates from the celebrity pool, merge sorting the two streams in memory in under 200 milliseconds. The only friction in this model is the cold start. An inactive user returning after weeks will have an empty Redis cache. They pay a one-time latency penalty as the system executes a heavy database pull to fully rebuild their timeline. Once the cache is warm, the hybrid orchestration holds. The write load is constrained to protect the message queues, and the read load relies on pre-computed lists to satisfy hundreds of thousands of queries each second. Global scale is achieved by mapping the mathematical limits of competing models and forcing them to cooperate at the edge.